slide gives you an overview of in-gel digestion process. We will talk in more detail about each of these steps as we go along in the next lectures, talking more specifically about specific type of mass spectrometry techniques. But today I am giving you sort of an overview, various type of concepts and various steps involved in performing the mass spectrometry experiments. So, in gel digestion, regardless of you have done the gel based proteomics or you want to perform the gel free proteomics, you can resolve the proteins on the gels, simplify the proteome, excise either the spots or the bands of your interest, and then subject those to the in gel digestion or in solution digestion, so that proteins can be cleaved into the small peptides, and these can be then further analyzed by using ionization source and mass analyzers. The slide shows you an overview of workflow involved in performing an MS based experiment. First of all, you can pre-fractionate your sample by using liquid chromatography, or one can also try different methods of doing the pre-fractionation and then applying that for doing the further MS analysis. After pre-fractionation, then in-gel digestion or proteolytic cleavage can be performed by using various enzymes such as trypsin, and then the sample can be injected into the ionization source, whether it can be ESI or MALDI, most commonly used for proteomics, as well as other type of ionization sources, and then these ions can be further resolved into the mass analyzers. Again, there are various type of mass analyzers, and then data can be analyzed in MS or MS-MS mode. Now, let us talk about different parts of the mass spectrometer. So, major components include the sample inlet, ion source, mass analyzer, detector, signal processing components, and data output. Let us look at each of these components in a little more detail. Sample inlet, it transfers a sample into the ionization source. The ion source or ionization source, it converts neutral sample molecules into the gas phase ions. Mass analyzers, it separates and analyzes mass of the ionic species. There are various type of mass analyzers available, which we will discuss in more detail during the subsequent part of the lecture. Now, one need to maintain the vacuum condition. A very low pressure is maintained inside the mass spectrometer. Detector measures and amplifies the ion current of mass resolved ions, and then we need electronics to control the operation of various units. The data system, it records, processes, stores, and help to display the data output. So, although there are three major components involved, ionization source, mass analyzer and detector, but then there are some accessory components which are also equally important for doing the mass spectrometry based experiments. So, what are different type of ionization sources involved in the MS analysis? The success of mass spectrometry experiment lies in efficiency of converting a neutral compound to a gas phase ionic species. So, you have various type of options currently available. You can select what type of ionization source you want for your specific application. So, the choice of particular ionization source is dictated largely by the nature of sample which one wants to investigate. With the gas phase, electron ionization chemical ionization and photoionization. These are the more commonly used ionization sources. With solution phase, electrospray, atmospheric pressure and atmospheric pressure CI, these are the more commonly used ionization sources. With solid phase, MALDI or matrix assisted laser desorption ionization, plasma desorption are the more commonly used solid phase ionization sources. The traditional ionization sources used for the small molecule chemical application relied on the chemical or electrical ionization, but these processes are too energy rich to ionize intact large biomolecules and they lead to the unpredictable analyte decomposition. So, for proteomic application, there was need for the soft ionization methods in mass spectrometry. These are non-selective fragmentation. The hard ionization is very difficult to predict. So, therefore, it led to the need of soft ionization methods in proteomics. What are different properties of ionization source? The main function of an ion source is to convert sample molecules or atoms into the gas phase ion species. The ionization source is responsible for converting analyte molecules into gas phase ions in vacuum. This has been made possible by the development of soft ionization techniques, which ensures that the non-volatile protein sample is ionized without completely fragmenting it. Most commonly used ionization sources are MALDI and ESI. Additionally, there are other ionization sources such as fast atom bombardment FAB, laser desorption LD, plasma desorption PD. Let us discuss the two most commonly used soft ionization techniques, MALDI and ESI, in more detail. So, MALDI is an efficient process for generating gas phase ions of peptides and proteins for mass spectrometric detection. MALDI is one of the most widely used ionization technique currently applicable in the proteomics area. This ionization method was independently developed by two scientists, Koichi Tanaka and Hillenkamp. Tanaka also received the Nobel Prize for his novel contribution into soft ionization technique such as MALDI. Let us first talk about matrix assisted laser desorption ionization or MALDI. So, analyte or the proteins of interest are mixed with the matrix, which is usually an aromatic compound. There are various types of matrices available, which we will talk in more detail when we come to the sample preparation and matrix selection. But just for your reference, we can use 2,5-dihydroxybenzoic acid, we can use cinepenic acid, and there are several other choices. Once you selected a matrix for the experiment, then analyte and matrix can be dissolved in an organic solvent, after which then it can be placed on the metallic target. As you can see in the slide, the first left section shows you how to place the analyte and matrix together on the sample plate. Now, once you have placed the matrix and the analyte on the target plate, you can put that in the vacuum chamber and apply high voltage. Now, these crystals are targeted with the short laser beams, as you can see in the slide. Then rapid sublimation can convert analyte into the gas phase ions. Now, these ions once generated, they can accelerate away from the target plate through the mass analyzer, which is time of flight TOF tube, and they can reach towards the detector. The various advantages and disadvantages of using MALDI as an ionization source. The sample preparation is very easy. The MALDI provides high tolerance to salt as compared to the electrospray ionization methods. The MALDI produces single charge species. Most analytes can accept the single photon. The single charge characters can result in some molecules having large mass to charge values. So, therefore, the MALDI is typically integrated with the TOF mass analyzers, which can provide the m by z range for the large ions as well. Now, these are various merits of using MALDI. Obviously, it has to be connected with the TOF. Now, there are various demerits of using the system. There is a strong dependence on how to prepare good sample for this analysis. So, sample preparation methods heavily influence the spectrum generated from these experiments. In MALDI, the analyte of interest is mixed with an aromatic matrix compound such as alpha cyano 4 hydroxycinnamic acid or cinnapinic acid. This is dissolved in an organic solvent and placed on a metallic sample plate. The evaporation of solvent leaves the analyte embedded in the matrix. Target plate is placed in a vacuum chamber with high voltage and short laser pulses are applied. The laser energy gets absorbed by the matrix and is transferred to the analyte molecules, which undergo rapid sublimation resulting in gas phase ions. These ions then accelerate towards the mass analyzer based on their mass to charge ratios. So, ESI, it requires sample of interest to be in solution. To ionize the samples, high voltage is applied to high conductively coated needle. So, this voltage results into the sample becoming charged either positive or negative. The positive ions are primarily used for the analysis of proteins. The distinguishing features of electrospray ionization includes its ability to produce multiple charged ions. The number of charges that can be accepted by a particular molecule depends on its basicity and its size. Now, here you can get an overview of the process involved in the electrospray ionization. The small droplet of solutions are generated by the Taylor cone, which contains the peptide analyte. Protons from the acidic solution provides droplets the positive charge, so that it can move from the needle to the negatively charged instrument. You can see this process with much clarity here in this slide. The top panel is showing the Taylor cone generation, and the center it is shown that production of multiple charged ions. Usually it is coupled to the MS via real time liquid separation. In electrospray ionization, the sample is present in the liquid form and ions are created by spraying a dilute solution of the analyte at atmospheric pressure from the tip of a fine metal capillary, creating a mist of droplets. The droplets are formed in a very high electric field and becomes highly charged. As the solvent evaporates, the peptide and protein molecules in the droplet pick up one or more protons from the solvent to form charged ions. These ions are then accelerated towards the mass analyzer depending upon their mass and charge.
The Agilent HPLC chip integrates enrichment and analytical columns, microvalve connections, and metal-coated nano-electro-spray tip on an inert multi-layer polyimide film, and is smaller than a credit card. The compact architecture of the Agilent HPLC chip reduces peak dispersion and combines all steps from sample loading through compound ionization for a seamless operation. A closer look at the HPLC chip reveals that sample enrichment and separation columns of a nanoflow LC system are integrated with intricate connections and nano-electro spray tip for compound ionization in mass spectrometry. This eliminates 50% of the traditional fittings and connections typically required in a nanoflow LC-MS system, which dramatically reduces the possibility of leaks and dead volumes and significantly improves ease of use, sensitivity, productivity, and reliability. The HPLC chip also incorporates all electrical contacts for the nano-electrospray tip and features an embedded radio frequency ID tag that tracks the usage and operating parameters of the chip. The chip cube includes an electrospray ion source with optics for spray visualization, HPLC chip loading and ejection mechanism, nano LC connections, and micro valve switching. The HPLC chip loading mechanism precisely and optimally positions the electrospray tip orthogonal to the MS inlet for maximum sensitivity and robustness, day in, day out. With the Agilent 1200 series Nano LC system, including microwell plate autosampler and loading pump, connected directly to the chip cube, an HPLC chip is loaded and leak-tight fluid connections are established automatically by sandwiching the chip between the rotor and the stator of the built-in multi-port microvalve. The rotor and stator dock onto the chip and establish a flow path from the Nano LC to the ports on the chip surface. Fast movement of the rotor ensures reliable switching between sample loading and sample analysis positions on the HPLC chip. Replacement of the HPLC chip is simple and can be completed in a few seconds. Let's look at how the Agilent 1200 series HPLC chip MS system can be applied to a typical protein identification analysis. The Agilent microwell plate autosampler loads the digested proteins. The solvent flow moves the peptides into the trapping column. The microvalve changes the flow path. The gradient flow from the nanoflow pump takes the enriched sample from the trapping column to the separation column. The peptides are separated just like on a conventional nanoflow column. Reduced peak dispersion yields better separation efficiency and sensitivity. The integrated nanospray tip ensures reproducible nebulization of the effluent, vital for optimum ionization of compounds and best results. Proven nanoflow LC-MS technology and the new and exciting capabilities of microfluidics combine to form a system that is easy to set up.
Let's have a comparison between MALDI and electrospray ionization and discuss their pros and cons, which can be used for the analysis of different types of protein samples. In MALDI, the sample analysis is for the simple peptide mixture, whereas in ESI, it can be used for the analysis of complex samples. There is a bias towards the polar or charged peptides in MALDI, whereas it is for the non-polar peptides in ESI. MALDI is more salt tolerant, whereas ESI is more salt sensitive. Liquid chromatography can be performed offline, whereas in ESI it is online and analysis can be coupled to the liquid chromatography. For the proteomic applications, the sequence coverage is less in MALDI as compared to the electrospray ionization. Both MALDI and ESI developments were awarded with the Nobel Prize.